cold or something. So bear with me. If you can't hear me, I'll, raise your hand or let me know some way. Truth in advertising, I'm no longer with Glaxo SmithKline, but all the work that I've ever done in green chemistry metrics and measures was done at Glaxo. So that's why I'm using their template. And my co-author, Conchita Jimenez Gonzalez, was actually supposed to be here at this symposium but couldn't make it. So I'll talk a little bit today about green chemistry metrics and data, and then describe some of the tools that we developed over the course of about 10 years within Glaxo SmithKline to try and give chemists and engineers at the bench level the ability to measure the greenness of their processes and synthetic routes. So very early on, from about mid-90s to early 2000, in the early days of green chemistry, there were a lot of people doing things that we were always bothered by the fact that they would say something is green, and we could never really determine from what they were saying is it really all that green? What is the rigor, the scientific rigor that they're using to determine whether or not something is truly green? And what we found is that people would choose one particular parameter or another and say, well, because it meets that particular criteria, it's therefore green. And when you broaden the aperture a little bit, what you find is it isn't really all that green. So it's really important. One of my favorite quotes here, I don't know how many of you were listening to John Warner, but he's talking about science fiction. This is a science fiction writer, and his point was is if you're not thinking about innovation and creativity as fiction, you'll never get there as scientific fact. So anyway, many people in chemistry and in science in general, I think, ask the wrong questions. And then they spend a lot of time trying to find the right answer to the wrong question. And I think that the early days of green chemistry in particular were rife with that kind of philosophy. People were just asking the wrong questions about whether or not something was green. So, somewhat humorous is that sign there, welcome to Pineview, Colorado. Clearly, that's where somebody's making a total out of 3 things that they shouldn't be totaling, right? And a lot of times, another quote early in the days of green chemistry, all he's done is call it green. And it's a very cynical remark that a person made in our company. Again, anybody could call anything green, and that's what you want to try and avoid. I'll just go up there. We've published a fair amount in this area. I've just listed at the bottom of this a couple of the publications that we did, again, early in the 2000s we published. So we came up after a period of many years with a few measures that we felt were key. What we did is rigorously dissect close to 100 different synthetic routes. So about 300 or more individual synthetic steps. And we looked at all kinds of different measures around those synthetic steps to try and decide which measures were the ones that were really key in driving the greenness of a process. So what I'm going to be presenting is really the distillation of that effort. To be perfectly honest with you, yield, if you come to my talk later this afternoon, I'll go into this in more detail. Yield is a compromise measure as far as I'm concerned. It's a very poor measure for greenness. And that in itself is a somewhat controversial statement to make with chemists, because most chemists say and are driven by yield. But yield really doesn't tell you a lot. Selectivity is important. The more selective your chemistry, obviously the less wasteful it will be, right? Particularly if you're talking about chiral and achiral type syntheses, selectivity is extremely important. Atom economy, Barry Trost, very early on, came up with this idea, A plus B equals C. Most synthetic organic chemists like atom economy. It's simple. The problem with atom economy is it completely ignores most of the reactants that are in a typical synthesis, and it doesn't include stoichiometry. So while it's a nice measure, it really doesn't tell you anything about the resource efficiency or the waste production of a particular step. And reaction mass efficiency was our answer to try and combine yield, atom economy, and stoichiometry. And so in our opinion, where we got to with our synthetic organic chemists, is reaction mass efficiency was a good measure from a synthetic organic chemist's perspective. But if you only focus on the chemistry, particularly if you're in a manufacturing environment, you only have half the picture. So you really need process measures. And again, after a lot of discussion and debate, what we found is that mass intensity is probably the best measure for determining the efficiency of your process. And it's really quite simple. For chemical engineers, it's a mass balance. It's everything that goes into the pot versus the kilogram of product that you come out with. So it's a fairly simple measure. The other thing that's included in mass intensity and is of interest is water. And I've made this point to a number of people. Water in the developing world, in many parts of the developing world, and in many parts of places like Australia, water is important. In the U.S. and in Europe, which is where most big pharma operates, most were not interested in including water. They thought water's free. But water comes at a cost, both environmental and at a cost, because especially in pharma, you use highly purified water. And again, water is also something that you heat or cool, and so you have a huge energy cost associated with water. So it's extremely important to include water. And then the other learning, which I'll talk more about, is really around solvent and solvent mass. Mass productivity is a percentage. It's just basically the inverse of mass intensity times 100. Why did we do that? It's easier for a business person to think about percentages, and that's the only reason we did it. Talk more later about life cycle and the solvent score. The other thing that we tried to include were measures of materials of concern. So again, this is really pre-REACH, and we were trying to get ahead of the curve and train our chemists to start thinking about substances that they should be driving out of their synthesis. John Warner said it earlier this week. It's been alluded to many times. The chemistry toolbox is full of absolutely nasty compounds. And we need to get away from those kinds of compounds into compounds that are inherently less hazardous. And, you know, a lot of people, Peter Myers was talking about risk and hazard and why it's important for us not just to ignore hazard and only dwell with risk. We can, in industry, safely handle hazardous, very hazardous compounds. There's no question of that. We've done it for years. But the question really is at what cost and why do we want to do that when we can, if we're creative and innovative, come up with alternatives that will require none of the control technology and none of the treatment technology that handling highly hazardous materials will require. So very early on, when we established the group within GSK, we got into life cycle assessment almost immediately. And the task that we were given was to come up with a way to do fully burdened life cycles on every synthetic process that Glaxo SmithKline developed within 10 years. At the time, that was a pretty tall order because there was virtually no coverage for the kinds of materials that you find in pharmaceuticals. And so in a given API production, you'll have hundreds of materials, potentially 115 to 200 some different materials. If you look at those materials all the way back to the cradle, you'll come up with hundreds of materials that you use. Each one of those comes with an impact. And again, do we want to be using materials that create such a huge impact in an API which is supposed to be having a human health benefit? The question is, we really don't. So we talked a little bit about materials. So what we tried to do is to influence development of the next generation, and if you're in specialty industry, it doesn't matter. The same would hold true. You want to do it in development as early as possible to affect the change. So it's in the very early parts of whatever the product development that you're doing. You build it in by design. You want information to be provided to the teams that are actually doing the development. So it has to be simple, and they have to be able to get these things themselves without a lot of extra effort. Life cycle is critical because, again, what you're handling doesn't come without impacts back into the supply chain. We collected metrics for every compound in development, and one of the things that we tried to say is the specific metrics that I mentioned earlier on, that's not the complete picture. You really have to have a broader view, and I'll get into that broader view in a little while. The other thing is that greenness, I made this point earlier on, I'd like to make it again. It's not a single or univariate exercise. It's a multivariate exercise, all right? And just because a process meets one or two criteria does not necessarily mean that it is a green process. A great example of that, get on my soapbox here, is catalysis. In the early days of green chemistry, a lot of people were working with indium chemistry. If you look at where indium is on the periodic table, and if you were at James Clark's presentation, indium isn't the most common element in the world. It's also a very toxic material. The same could be said around many of the platinum group metals, ruthenium, palladium. All of these metals come at a very high life cycle impact cost. And it's going to become increasingly more difficult for us to obtain those particular materials. So the question I have for aspiring green chemists is that really the area of catalysis that we should be looking at? And my personal answer is no. We should actually not be looking at metal catalysis unless it's something related to iron or some kind of transition element that's as abundant as iron. So our commitment within the company was to develop a series of tools, and I'll just go through these to show you, to give you some idea of what's possible. Obviously, not every company is going to be able to have the time and effort, and these tools were literally created over about 10 years. So it was a sustained effort to do it. There were multiple iterations of them, and they're fairly well developed. That does not mean that you can't do something much simpler. Everything that I'm showing you here, which is a web-based system, started out on a spreadsheet. Okay, so you can get as simple or as sophisticated as you need. It doesn't have to be this sophisticated. Green chemistry guide that we created really was based on that evaluation of chemistries that we did. And what we tried to do was to provide chemists with an idea of which chemistries, out of all the chemistries that they were typically using, were greener. And again, we went through a very rigorous process to evaluate what was green. Again, what we tried to do is distill everything down to a single graphic, a single page from which the chemist could go very quickly make a determination of what kind of chemistry they were using, and then, like peeling back layers of an onion, dig slightly deeper to understand what was driving the particular lack of greenness. So you'll see on the left-hand column the type of bond that was being made. all right? So whether it's a carbon hydrogen, carbon oxygen, general